We introduce Feature2 Gaussian, a unified framework that probes the texture and geometry awareness of visual foundation models. Visual foundation models are often trained on 2D images, but how well do they understand the 3D world? To answer this question, we need 3D probing. So, what is 3D probing? Typically, it involves training a network to regress depth or surface normals from the features of visual foundation models. However, these methods rely on 3D ground truth for evaluation, which limits the scale and diversity of their evaluation datasets. This got us thinking, can we only use 2D data for 3D probing? Yes, we can, and novel view synthesis could be used as the proxy task. We evaluate 3D understanding of the features by doing a 3D Gaussian reconstruction. To achieve this, we use a lightweight readout layer that is fine-tuned with photometric loss from casual multiview photo captures, such that we can evaluate 3D awareness of these foundation models, using novel view synthesis on diverse, open-world images. Before diving into extensive analysis, let's validate our key motivation. Is novel view synthesis equivalent to 3D metrics? We conduct experiments on the DTU dataset, which has dense point clouds as 3D ground truth. We compared novel view synthesis results with point cloud error map. Note that good rendering quality reflects the low error map, and vice versa. It shows that 2D metrics align well with 3D metrics, supporting that novel view synthesis as a proxy task for 3D evaluation. Next, we evaluate mainstream visual foundation models across diverse multi-view datasets. To analyze geometry and texture separately, we group Gaussian positions, opacity, and covariance as geometry parameters, and spherical harmonic coefficients as texture parameters. When probing geometry awareness, geometry parameters are regressed from visual foundation model features. Simultaneously, texture parameters are optimized freely. Here, the discrepancy in novel view synthesis reflects how well or bad these visual foundation models capture geometry. Notice that the differences in the locomotive, logos, and louvered windows. Pay attention to the differences in the tire and cab. Compared to Dino V2, Dino obtains a more complete bucket. We show different aspects of geometry awareness. Position awareness is typically reflected in the sharpness of readout details, such as the AC units, windows, and building edges, while covariance awareness is often observed in the flatness of planes. Stable diffusion shows the weakest geometry awareness, with broken geometry in areas like the pavement. The rendering quality of novel view synthesis can efficiently reflect normal and depth accuracy. Then, turn to probing texture awareness. We regress texture parameters from features, and freely optimize geometry parameters. Interestingly, we found that while recent visual foundation models capture geometry well, they still struggle with texture. Note that these models even perform worse than the raw image feature IUVRGB. When probe both geometry and texture, we simultaneously regress all Gaussian parameters from features. Notice that the renderings from all models are blurred. Optimizing just geometry yields better results, highlighting the lack of texture awareness in current vision models. Based on our observations, we design a strong baseline by reading out geometry from features for novel view synthesis. Compared to the current state-of-the-art, instant splat, our Feature2 Gaussian produces more consistent results thanks to the inherent alignment of features from different views. Our Feature2 Gaussian not only has better novel view synthesis quality, but also better normal and depth renderings. Welcome to our website. Check out our online interactive demo. You can play with it right now. Thanks for watching.